Our next talk is by Jim Anderson, and it's on feedbacks in the climate structure that set the timescale for irreversible change, coupling climate forcing and catalytic chemistry.
So I have 20 minutes of stories about Dr. Barth, and then I've got the scientific presentation.
You have 2 minutes
I've got
left.
2 minutes. This is the way it always is. But I want to talk about this issue of climate feedbacks that set the timescale for irreversible change in the climate structure. And of course, we've seen this picture a number of times before. The minute I saw it, I thought, this is the ideal memory, because I arrived in the fall of '66 intending to study radio astronomy. I held a conservatory and had an NSF fellowship, paid $200 a month. And at the end of the year, I was broke. And so I walked to Dr. Barth's office and I said, would you write me a letter of recommendation to Ball Brothers? Because I had a month off, I'm allowed to work for a month. And in this kind, gentle way, he rocked back. I just imagined what he was thinking. But he remained calm and he said, you realize that Ball Brothers has a 3-week training period before anything begins. You think they're going to hire you for a month? He said, well, look, don't worry about it. Just, I've got a lab upstairs that's using UV spectrometers. Just work for the month and I'll pay you. So I went upstairs. This is the old LASP building, of course. The main lab is in the middle of the second floor, and in the lab was Ken Kelly and Jeff Pierce. And after 3 weeks of that, I never thought about radio astronomy again. And I asked, by that time, Charlie Barth, if I could join his group. And he said, of course. So the next vintage Barth move was, we took this comprehensive exam, which was this draconian thing where I tried to flunk graduate students out, which served no purpose that I could see, but I passed it. And rather than calling me in and saying you passed, it's fine, these 2 rocket contracts appeared in my mailbox. And so I walked into Dr. Barth's office. I said, I think there's been a mistake. There were 2 rocket contracts in my mailbox. And he said, no, it's no mistake. They're yours to do with what you will. I said, really? And it came with instrument development and everything else. I mean, this was close to $1 million in current dollars. So I told him how profoundly appreciative I was. It was the finest gift I've ever received at any time from anybody. And so I went home and I thought about this, and I went back in and I said, could I use the rocket to look at the hydroxyl radical instead of nitric oxide? And I expected him to say, well, really? But he didn't bat an eyelash. He said, of course. Fine. So here's the picture of that. This is a Nike Apache, and I was really furious that it just didn't make the listing of NASA rockets. So, Bill, would you like to stand up? There's Bill. This is Yvonne Meira, who is in Brazil and has been very, very influential in Brazilian space physics. But this is at Wallops Island. They launched this rocket, which set an upper limit on OH. And the next slide is this. Somebody said magnesium doesn't show up in the Earth's atmosphere. And honest to God, I didn't just slip this slide in there.
No. Barth's in my reference list.
Okay. So that OH experiment happened to scan over the atomic emission of magnesium-1 and magnesium-2. These were huge emission lines. I flew right under a sporadic E, which, of course, this is a meteoric deposition. But Charlie Barth knew instantly what they were. And he said, this is really exciting. This hasn't been observed before. And so I decided, well, I'm going to write this paper in 1 week, which which I did, and went out for review. Don Hunton got it to review. Now, many of you know Don Hunton. I mean, this was a catastrophic collision between the green graduate student and Don Hunton. And he said, this is a great observation, but the paper reads like a stream of consciousness. So I went back and fixed it. Anyway, this is my first paper. Very proud of this. I think it's in the listing outside. Okay, so then, now Diane Anderson took this picture. This is her Broida. This is Charlie Barth. This is Ted, I can't remember his last name, he was an engineer. And this experiment polarized the spectrometer and it spun so it could modulate the Rayleigh scatter. And I moved to very high resolution and a very short scan length. And that required setting the instrument up on low temperature hydroxyl. And Herb introduced me to laboratory experiments where you discharge species to form free radicals. And I just became completely enamored of the laboratory work on this. And so I flipped hard over to Pittsburgh with Kaufman working on free radicals. But Herb really was a crucial contributor and a great partner. He was at Gilla. Okay, so I'm going to turn now to this question of the climate structure. This focuses on the Arctic, and Bob has already mentioned how important the Arctic is, and it's very clear when you look at the structure of climate that as goes the Arctic, so goes the entire climate structure, because there's a cascade of feedbacks that come off of changes in the Arctic, and the Arctic is changing really quickly. So this is the volume of permanent floating ice, that is the amount of ice middle of September at the end of the melt season. And these are microwave data, but the University of Washington combines the area with measurements of depth to provide for volume measurements. So this is 1,000 cubic kilometers. Starting back, it's about 17,000 cubic kilometers in 1979. Now we have the data running all the way back out to the mid-50s because the atomic submarines actually mapped it, and then the topography was so stable, nothing was changing. And of course, when we started cruising, we needed to know what the mountain ranges looked like inverted. But even in 1979, 17,000 kilometers, and it's dropped now down to 2 or 3 just in the past 30 years. This wasn't forecast, it wasn't understood. In fact, in 2007, when the IPCC report came out, there was less ice in the Arctic the month the ink dried on that report than it forecast at the end of the century. And that's how bad those forecasts are. And this is a really serious problem because when you lose the permanent floating ice in the Arctic, we begin to change the temperature structure. The temperature gradient between the equator and the pole is absolutely essential for setting the overturning rate that dictates the entire climate structure. And so this also couples back into what Jack Barth is talking about. This isn't a matter of global warming. His point was, this isn't planet Earth, this is planet ocean, because the oceans are 3.5 kilometers deep, 7% of the Earth's surface. Huge heat capacity. The last thing that changes is temperature. And the idea, 2 minutes, oh, look, I'm toast, I might as well quit. Oh, God. I can't even know what I was going to say. All right, anyway, very important to the climate structure. The feedbacks are numerous and they're potent. One of the key feedbacks is the release of carbon. The University of Alaska is doing a lot of work on this. This is a clathrate, which is a beautiful water structure with methane in it. There's 3 times as much chemical energy tied up in clathrates than all known fossil fuels. It's all coal, natural gas, and petroleum. And just 0.5% of the release rate out of the upper 2 meters of northern Alaska and Siberia, 0.5% of that per year equals all carbon added from fossil fuel combustion. So this is a really potent feedback. So we've developed instruments that fly on very small, very lightweight aircraft which can be flown either conventionally or by a robot. There's a robot that sits in the front seat, the pilot sits in the left seat. You flip a switch and it can fly robotically or conventionally. And drill this integrated cavity up, and spectroscopy gives us about 5 kilometers of absorption length and half a meter. And this gives you this gorgeous absorption spectra for all of the isotopes of CO2, methane, we can do CH3D. And the isotopes tell you the origin, flux of carbon dioxide and methane coming out of highly idiosyncratic regions that are melting down in the Arctic. And so here's a shot. We fly the airplane just 5 meters above the surface, so it looks like that. And that gives us spectacular spatial resolution. And that spatial resolution is very important because we have to identify the character of where that carbon is coming from. So I shot these pictures with my iPhone. This is the oil pipeline coming out of Prudhoe Bay. And this is intercalibrated with NOAA towers. And the next passage, I stepped out to take a picture. I know I'm 2 meters high, and I know the plane is 5 meters high, but it took all my intestinal fortitude to get down. There's exquisite detail in what's coming out, and we measure both the flux and the concentration of all the isotopes. Because I'm profoundly concerned about this feedback structure. You can see all of the information resides in the lower 40 meters or so of this. Okay, so climate feedbacks couple this emission of carbon from the permafrost and clathrate back into the system. And that drives Greenland glacial loss. It drives the loss to the glacial structure, but it also affects the large-scale climate structure in a very significant way because the water vapor pathways that Mary Barth is studying, the convective injection, has a profound effect on change in climate structure. So Greenland, for example, the meltwater has increased. So in 2012, the entire surface is melted, but the water doesn't just roll off the back, it goes through fissures down to the base, and the entire stability of Greenland is determined by the bond between that ice and the bedrock. So any horizontal slippage leads to the collapse of the system. It's not going to melt, it's going to collapse. Just to show you, this is Charles River Basin. This is Harvard's property in yellow. They're planning on dropping $10 billion on a new campus right here. So I'm going to add just 40% of Greenland's ice volume. And that's what it looks like. And you know, alums of the university actually read, and they're starting to say, I'm going to donate $100 million, and you're going to be underwater in a quarter of the lifetime of the university. Now, I should point out that fortunately MIT goes under. Other than that, there's no good news. And all these coastal regions are now susceptible to this. Now, I'm going to just end with how my work couples into Mary's. It starts in the Antarctic. This, of course, is the Antarctic ozone hole. We started using this U-2 spy plane. And Bob Watson, by the way, was a compatriot in this. He set the mission up. And it was the anti-correlation between ozone and CLO inside this chemical beaker that's contained by the polar jet that set in place the mechanism responsible for the Antarctic. Well, we did the same experiments over the Arctic. This is when we flew from Kiruna, Sweden, in over Russia. This is the first time the U-2 had gone over Russia since Gary Powers was done in 1958. And so I worked with, I was a mission scientist, and I worked with the Russian generals, which later on, I'll tell you the story, I don't have time. But the key thing here was the same anti-correlation between the rate-limiting radical CLO in red and ozone in blue exists over the Arctic, except there was a fundamental difference. Over the Antarctic, it was believed that polar stratospheric clouds catalyzed the conversion of inorganic chlorine to free radical form. Well, over the Arctic, we discovered that it was actually simple sulfate water, binary aerosols that triggered this conversion. And binary sulfate water aerosols are ubiquitous. They're everywhere in the lower stratosphere. And we thought it was just an academic discovery at the time, but what it did was it put a second dimension into this problem where it's not just a function of temperature, where you go from the white region where there's no conversion of inorganic chlorine to periodic form to the gray region where there's complete conversion. This is really getting serious.
Yep.
Okay, well, so the hell with it. I'm going to go to the last slide with all of this really interesting stuff. And I'm going to focus on one last. This is
a lot of slides.
so interesting. Okay, so back to Charles Barth. I just want to point out what he taught me implicitly and explicitly. First one is never utter the word no. In fact, I don't think the word exists in his vocabulary. Has anybody ever heard him say no? I just kidding. Yeah. As soon as I posed the question, I said, I believe this one. Okay. That was lesson number one. I never heard him say that. Don't micromanage people. That's another crucial lesson. Give students challenges that have no hope of accomplishing. Step back, watch to see what happens. Great things can be accomplished with a small number of superb scientific objectives. This was a lesson I was reading. When you have something important to say it softly, and say it gently. That was my experience. Ignore inappropriate, misguided, immature behavior in graduate students. And I can tell you, I tested the outer limits of this one. And he never flinched. And I've had 35 graduate students, and none of them behaved as badly as I did. If it's been done before, it's not worth doing. And then contrast that day with today. We have these massive problems in the climate structure. These gliders that Jack was talking about are absolutely crucial for mapping the entire ocean. And we're looking at a tiny, tiny fraction of what we need to in order to forecast the climate in an accurate way. And here we have massively more difficult challenges. And the one slide I hopped over is one that where I proposed to NASA to use the fact that the anticyclonic flow over the United States can trap not only the convectively injected material that Mary was talking about, but it allows you actually to navigate a solar electric propelled superpressure balloon with impunity in July and August. So you can have 6 weeks of observing time, whether it's a telescope or whether it's a reel down system that we developed that lowers an instrument package on the Kevlar film at 10 kilometers multiple times a day. So it can be used for earth science, planetary science, or for astronomy. And I'm sorry I ran over. Sorry.